12 modular function is tempered. Sataki. And so a couple of people had questions about how he did that and what steps he went through. But it's in my memory, if memory serves, it's one of the early articles in the Boulder conference. One of the sort of introductory articles in the 1965 Boulder proceedings. Namely, that's the argument that classical Ramanujan for pi, I guess it's an if and only for a delta, if and only if the corresponding automorphic representation is tempered. Maybe the right-hand side is perhaps a little stronger because it includes the Archimedean component of this as well. And as such, it applies to eigenvalues of the Laplacian on the upper half plane. Oh, all right, so Langlands at the very end of his article on Boulder had, I mentioned, he had 4 consequences. I mentioned the one, the analytic, that functoriality implies the analytic continuation of L functions, the general automorphic L functions, 1. 2, it had implied non-abelian class field theory in the sense that it attached automorphic representations to Artin L functions and representations of the Galois group. But then I mentioned then there's a third and a fourth one. The third one was applications to Ramanujan's conjecture. This was actually before Ramanujan's conjecture had been solved by Deligne, and Langlands actually pointed out an argument that solved it. This is this viewed in this language. It's remarkable as this inequality of Ramanujan's is. You see, one sees from this that there's major generalizations of it available, namely, what about general automorphic representations? And Langlands gave a sketch, 1.5-page sketch of why functoriality would imply that as well. And it's quite a brief argument, and I struggled with it the last couple of days. So F3, this is functoriality. Would imply generalized Ramanujan. So I'm going to try to give a sketch of Langlands' argument. And it's I just say again, it's the last page or the last page and a half of his Bachner article, right at the end. So let's do it in this context. Suppose I'm going to copy Langlands chose what he said was a very special case, but of course, it's quite a lot more general than this, but a very special case. It was in the sense of general automorphic forms, suppose that G, first of all, we'll take it over Q, is split, a split group, and that pi is a cuspidal automorphic representation of GA, and the conditions that he put on it, that's simply because he hadn't really even set up some of the things, although I think he had them in mind, but he hadn't set up some of the things that would apply in red ramified places. So in the same spirit as Ramanujan delta function, he assumed that it was unramified at all valuations of Q. And so in particular, the exceptional set of valuations, S, consists of infinity alone. In other words, it's just the real valuation. Langlands actually includes in this assumption that it's unramified at the Archimedean place too, which I guess means it's just an absolute value on the reals. So you're looking dubious, Kumar. No, that it's that in a natural sense, it is that the representation pi is unramified at the real place as well. So we'll say. Can you have something which is unramified everything? Which is which? Unramified everything. I think what he means by this, unramified everywhere. Even at infinity? I assume it holds in the Ramanujan case, does it? By unramified, I mean that it's as a representation, for example, of GL1, it's just GL1R, R star, it's the same. It's the same on the negative reals as it is on the positive reals. I assume that's, I hope, well, I didn't investigate how general that was, but I assume that's probably the case. I would assume that's the case for the Ramanujan tau function as well. Isn't that ramified at infinity? The Ramanujan tau function? Oh yes, it is. Of course, it's a discrete series at infinity. Yes. So yeah, I'm sure there's lots of cases like this. It really is just to avoid the arguments, to me anyway, complicated enough as it stands, and this really was just to avoid further conditions to be drawn at ramified places. Okay, so what he assumes, that's what's given. I mean, you could have in the upper half plane, you could have something that's just at the Archimedean place. You could have something for the upper half plane which is on SL2 on the upper half plane modulo the full congruence, so the full modular group, and it is. But it's just I'm at a loss, right? I've been spending too long thinking about these things, and the words don't come.
Yeah, no, I understand that unramified at finite primes means it's level 1.
That's right. And at the Archimedean place, it is just I guess there's no lower half plane. It's the same at the upper half plane as the lower half. Yes. Yes. I think so, but I didn't go. I'll warn everybody. I haven't really been through all of the fine points of this, even though for I think an expert in L functions, they're not terribly complicated. But the assumption for this, which is basically functoriality, is that the automorphic L function L of S I sigma, the full product. So by this now I'm taking the full product over all valuations of the local L functions, S pi sigma, is analytic. For the real part of S greater than 1. For every representation, sigma of the dual group. So V over C is a complex vector space. So we're not really assuming the analytic continuation and functional equation. We just have this. But that I think is probably would be difficult if you couldn't relate this to the standard L functions. So this would follow, in particular, this would follow from functoriality. In the way that the first one followed when we attached an automorphic representation of GLN to a representation of the dual group and an automorphic representation of some other group. So this would follow from functoriality and the Godemont-Jacquet theory. Theory of standard L functions. For GLN. Okay, so how to set it up? To set up the argument, we've got a split group. And so we'll fix a Borel subgroup. So this is, we have to set things up actually in the dual group. So let's just stick with that. We want to fix a Borel subgroup of the dual group and a maximal torus. T hat inside the Borel subgroup. That's a complex torus. Now, what do we have also an automorphic representation, and so that's the automorphic representation pi of G. This is the arbitrary, the split group, GAF. And remember that I think we really only described this explicitly in the case of GLN, but the data that you would attach to an automorphic representation, especially one that's unramified everywhere, is simply a family of conjugacy classes, semi-simple conjugacy classes in the dual group, which we would intersect. We wrote them for GLN, and we had a diagonal matrix of eigenvalues at each p. Well, here you're just going to have, you would intersect these semi-simple conjugacy classes with T hat. And so what you would get would be a family CP pi. Remember, we fixed an automorphic representation, P prime, This is the automorphic representation that we would like to try to establish Ramanujan's conjecture for, in particular to establish that it's tempered. By the way, I should say the problem is that the automorphic representation might not be tempered. That's what you're trying to show doesn't happen. Automorphic representations, cuspidal automorphic representations, yes, I assumed it's cuspidal, but cuspidal automorphic representations, they're unitary, but we're used to thinking of them as having unramified pieces. Tempered pieces, pieces that come from purely imaginary conjugacy classes in this torus. And that's not necessarily true. There's lots of unitary representations, the so-called complementary series for GL2 and analogs for more general groups, in which you, at the various primes, and you don't know, we don't know, no one knows that whether a cuspidal automorphic representation, for all we know, might have little nasty little tails on it that make it non-tempered. Little, it might, at the unramified places, it might have little little pieces that make it non-tempered. The point of this, that they would, by the way, also impact where the domain of convergence is. And so for the L function. So that's why this assumption is important. It's ultimately to rule out, to show that there's none of these little little bits attached to the various unramified places, which are all places here, show that we want to show they don't exist. That's the same thing as showing that the representation is tempered. The automorphic representation is tempered. At each, the notion of tempered is usually spoken of as a local notion, and so we would want it to be tempered at all places of Q. Okay, so that's what we're working on. So anyway, P gives us a set of, for every prime, it gives a set of semi-simple conjugacy classes for each prime, a semi-simple conjugacy class in G hat, which as semi-simple, we can intersect it with the maximal torus, and then it'll give several points in the maximal torus because there'll be a Weyl group acting on it. But in any case, it's so this would be these things. We'll be thinking of these things as the intersection of T hat, this maximal torus, with each one of these is the intersection of T hat with a semi-simple conjugacy class in G hat. That's what the Hecke operators give you, and it's so remember there were two ways to think of where this thing would arise, namely in the construction of a representation pi p, an unramified representation at a p-adic place. Question? No. So remember, these conjugacy classes come in two equivalent ways. One, they're the data for which the induced representation that represents a non-standard representation pi p, these are the inducing data, but they're also eigenvalues of the Hecke algebra, which in this adelic formulation is at a given place p, is the convolution algebra of smooth functions of compact support that are bi-invariant on G Q-adic, p-adic, which are bi-invariant under a maximal compact subgroup. So anyway, that's where these data come from. And so we've we're talking about, now we're talking about representations in addition to pi, we're talking about representations sigma of g hat. So find these finite dimensional representations of a split group. So given sigma and v, the representation that we're going to use, pi is fixed, but what we're going to do is vary the representation sigma to try to squeeze pi and show that pi isn't hiding any unpleasant secrets, namely that it's got some bits that are making it non-tempered. So given sigma v, we will let lambda be the set of weights of sigma on T. Sigma is a representation of G hat. There's a maximal torus in G hat, and finite dimensional representations of groups come from highest, or parameterized by highest weights, and the set of all eigenvectors or the set of all weights parameterize the vectors in the space V that supports this representation. So let me say it like this. It's a set of weights. I'm going to say repeated according to multiplicity. Okay, so repeated according to multiplicity. So in other words, i.e. these weights can be used to parameterize so it parameterizes a basis. So it parameterizes a basis v lambda of v, such that, so this is a basis of not just a basis of vectors on v, but a basis of eigenvectors of the representation sigma restricted to the maximal torus. So sigma of t v lambda equals lambda t equals lambda t. So lambda, these are these are functions, these lambdas are functions on t hat, they're characters on t hat. So sigma of t v lambda equals lambda of t v lambda for every t in t hat. I'm using Langlands notation. These things are weights, they're characters, they're characters on t hat as a torus. So they're usually, these days, they're usually written exponentially, but Langlands writes them as simply characters like this. So we'll be following that, therefore, where each lambda t hat to c star is a character, quasi-character. So the problem, I'll welcome any interventions. I thought about this all of yesterday, but I can't say as I really have a grip on it. But the problem is to show that each of these elements in t hat, these CP pi's, taken up to conjugation by something in the Weil group, lies, I want to know, this is a characterization of temperedness at a given local place. It's a characterization of it in terms of the things that parameterize the representation. And so the characterization is, this Langlands actually pointed this out, I think, in that article. One wants to know that CP is not just an element in T hat, but, or more basically a semi-simple conjugacy class in T hat, but rather that CP lies in the maximal compact or a maximal compact subgroup of G hat. Okay, G hat's a complex group. It's got a max, it's got a, if it's a GLN, if G hat, by the way, the case of GLN is certainly very relevant here. G itself would be might be a smaller general linear group, and then sigma would be a mapping of that smaller dual group into GLNC. But in any case, if G hat, if we were dealing with a general linear group, then we'd be talking about the unitary group sitting in this complex general linear group. And that's what we want to show. We want to show that each of these conjugacy classes actually lie or meet, let's say, a given maximal compact subgroup of G hat. Okay, so I want to show that their intersection lies in the compact part of T hat. In other words, we would like to show that any one of these algebraic characters or weights, CP pi, lambda CP of pi, has absolute value 1 for every p and lambda. CP, if you were dealing with GL2, T hat would be C star, and you'd be talking about lambda being characters on C star, and CP is an element that lies in C star. You want it's a little piece. If you're dealing with SL2 or GL2, CP's a little piece, or if it were just that small group, it's everything that governs what the induced representation pi p is. And you want, as a parameter that governs this induced representation, you want it to be unitary. You want it to lie not in C star, but the set of complex numbers of the form e to the pi I theta sitting in C star. That's what we have to show. That's what we need to be able to say that pi p is tempered. Okay, to do this, what we have to do is must study. All we've got is the absolute convergence, or all we've got is the analyticity of the L function attached to any given sigma. So what we have to do is to study it. Okay, so we've got the L function, Ls pi sigma. And I'm writing this down now. We've been writing, up until now, we've been writing it with an upper S, leaving out the ramified places. And the set of ramified places included the Archimedean place. I'm not going to have that anymore. And so I'm going to write L infinity, the component of this L function, the Archimedean place, sigma, and then the complement, the L function given by the complementary local factors, L upper infinity, Ls pi sigma. So this would be L infinity, or let's just write it as Ls pi infinity sigma infinity. Well, sigma infinity is the same as sigma. I would only attach a subscript to it if there was a Galois piece in the semi-direct product that forms the L group, which we're not going to do. We're going to be taking the field E extension that Langlands puts in general, the E over Q. I'm going to take E to be equal to Q, which I can do if I'm dealing with a split group. So sigma infinity, the notation really there is not necessary. But then the Euler product of S pi p, let's write it just to be orderly. We'll write that as sigma p, even though sigma p is the same as the sigma. Okay, now I'm going to have to just write something down that we haven't talked about. In fact, Langlands didn't really set this. He really didn't define these things. What I'm going to have to set up is the Archimedean component of the L function. Langlands did not define it. He I think knew more or less what it would be in the most general situation. But he said that's just, earlier in the paper, he said it's just a product of gamma functions, and without being specific. But in this case, he wrote down what it would be. And so I'm just going to write that down. I hope we'll have a chance to get to this a little bit later. It comes from the data attached to representations of real groups coming from maps of the Weil group into the dual group. So the point is that the representation, so I'm just taking this as for granted, the representation pi infinity of GR comes with a semi-simple conjugacy class, just like we had for the p-adic groups. It comes with a semi-simple, and I'm using, to be able to state this, I think I'm using the fact that pi infinity is unramified at the Archimedean place. So that comes with a semi-simple conjugacy class actually in the Lie algebra, G hat, of this complex dual. So it's the complex Lie algebra G hat of G hat. So in other words, it is a G hat orbit x infinity in the Cartan. So it's the intersection. It's a G hat orbit in the Lie algebra. And so it's G hat orbit this is not quite correct, is that what I'm saying? But it's a G hat orbit intersected. Let's say the intersection so the intersection, I will write it as x infinity of t, the Lie algebra of t hat, so it's t hat, the Lie algebra of the capital T hat in G hat. So the intersection x infinity of t hat with a semi-simple with a semi-simple orbit of g hat in the Lie algebra. G hat, of course, acts by the adjoint representation on the Lie algebra, and so I think I've bungled the language here. Anyway, it comes with an element x infinity in the Lie algebra of g hat. And what one wants is the same thing. One wants to know, Ramanujan would say, that this lies in the imaginary part of this torus. But the condition we want at the moment is that L of S pi infinity R infinity is equal to the product over lambda. These form a basis of the action of t hat. These form a basis of the vector space V on which g hat acts. So it would be the product over weights lambda of, this is a product sign, of little pi to the minus s plus the differential of one of these characters. It's supposed to be, this is supposed to be a linear function on the Lie algebra t, x infinity. And so these, I'm sure, would be familiar to many people now, but then the power of pi, including f, that includes s, with a gamma function, gamma of s plus d lambda of x infinity over 2. That's the gamma function. So it doesn't really matter too much what that is for present purposes. This is a product. This is a product over all lambdas. And the point is that this is non-zero. That's the main thing that we want to know for every S in C. The reason it's non-zero is, I'm just copying, I didn't bother to look it up, and I don't carry gamma functions around in my head, but it's just copying Langlands' assertion. It's because the gamma function doesn't have any zeros. So since gamma function is never zero. All right. I wonder if I want an inverse on this. I can. No, I just, no, I'm fine. So L upper infinity is the complementary piece. So that's the Archimedean part of the local L function, of the global L function. And what's left is the product over all P, which we're denoting as L upper infinity of S pi sigma. Our original assertion or hypothesis was that LS pi sigma itself was analytic for real part of S bigger than 1. Now, I don't want to have to deal with the Archimedean part. So I'm going to take it away and just study L upper infinity. But it's important to know, if I am doing that this thing is never zero, because then if it were zero, then this thing could possibly have a pole for real part of S bigger than 1, and I'd lose my assumption that it's analytic for real part of S bigger than 1. But it's never zero, so I can say that LS pi sigma is analytic for the real part of S bigger than 1. Because of that, by our original assumption. And so this is an assumption that comes from by combining functoriality with the Jacquet-Godemont L functions. So we want to look at this thing, which is standard fare for analytic number theorists. Not so much for me, but LS pi p sigma p. We're thinking of the product over all of these p-adic components. So that's the determinant of 1 minus sigma Cp p to the minus s to the minus 1. And so that is this is an operator on this vector space, complex vector space V, on which we have singled out a basis parameterized by the weights. The weights give the eigenvalues of this operator, and so that this is the product over all of these weights. Remember, they're repeated according to multiplicity, and this is 1 minus lambda sigma Cp. Okay, we got to take lambda of sigma Cp, p to the minus s to the minus 1. Okay, we're just evaluating the determinant as a product of over lambda of these polynomials. The determinant's a product of polynomials, 1 minus parameterized by the weights. So it's a product of these polynomials. So the determinant is equal to this product over lambda. And so we can write the finite part of the L function, L upper infinity, S pi. So this is, forgive me for my going slowly. It's but that's the product over all primes, the product over all weights. This is a finite product of 1 minus lambda sigma Cp. I have to write, it's complicated enough. I have to make sure I try to write neatly. Lambda sigma Cp, p to the minus s to the minus 1. Okay, so that's what we've got left. And we want to how am I doing? Oh my goodness. What we want to do is to be able to exploit the given information that we have, our assumption. So we want to construct from this another Dirichlet series. by taking the logarithm. Okay, so we get that the log of L infinity S pi sigma is equal now, so these products become sums. So we get the sum over P, sum over lambda of log of 1 minus lambda sigma Cp P to the minus S to the minus 1, which is equal to the sum over P, the sum over lambda, and the sum from n going from 1 to infinity of 1 over n. So we just we'll take the expansion as a power series of log 1 minus a variable. So this would be 1 over n lambda of the operator, not sigma Cp, but rather sigma Cp to the n. And then P to the minus ns, because logarithm of 1 over 1 minus u is the sum n going from 1 to infinity of u to the n over n. I'm not worrying about convergence. All of these things we're in a domain where they converge. And so this is equal to, okay, now we have a sum over the lambdas of these, over a basis of these operators raised to the nth power. So this is a basis of the vector space on which these operators act. So it's the sum over P, the sum over n of 1 over n. Well, these things are just the traces. This is just the trace of the operator sigma Cp to the n, P to the minus ns. So this is the formula. This is the formula for the logarithm of L infinity S pi sigma. Now I'm not going to be able to quite finish this today, but so I'll bring this one down. How much? I have a couple of minutes. Yeah, I've got 5.5. I've got 5 seconds left. Okay, so the point is, we're almost there. The point is then to take sigma to be of a particular form, to take sigma to be a tensor product, not just any old representation sigma, but a tensor product of a representation with its contragradient. And that means that the trace becomes a positive number. And that means that the coefficients of the Dirichlet series for this Dirichlet series here, it means the coefficients, if you take this very particular sigma, means that the coefficients of this, did I forget to write down the trace? think that's not what I wanted to. Yeah, it's this one. That's the formula that I wanted. Okay, so it means that the Dirichlet series for logarithm of L infinity has positive coefficients. And there's a very theorem I didn't know, but I guess a very relevant theorem that applies to Dirichlet series with positive coefficients. It's called Landau's theorem, and it says if you have a Dirichlet series with positive coefficients, then the domain in which it converges absolutely, I think it's called the abscissa of convergence for its domain of absolute convergence, has a pole at the real point on that line. Oh, singularity, I see. So that could be a irregular singularity. Ah, I see. I see. Okay. All right, but so then it has a singularity. Now we know that this series is analytic for real part of S bigger than 1. So it means there's going to be a singularity, and then I guess so the this proves that the exponential of this, namely the origin of that name on the right-hand side, namely the original Dirichlet series, I guess also has positive coefficients and converges. So it would have a pole at its well, a singularity anyway. It doesn't matter. A singularity at the real point on its abscissa of absolute convergence. And so we would use that to show that there's absolute we want absolute convergence for real part of S bigger than 1. So we're going to use that. All we have to bear on that is the analyticity of this L function for real part of S bigger than 1. But I want to show if there was a pole to the right of the real part of S equals, if there was a nasty piece, if the representation was non-tempered, it would mean that there was a pole to the right of the real part of S bigger than, the real part of S equals 1. And so this is what allows us to rule that out. So I'll finish it next time. I thought I'd read that, but I hadn't really read. I misunderstood.